let us now focus on the operations on the independent variable. And the most common operation that you encounter when it comes to operations on the independent variable is what's called the affine transform. That is, it consists of both time shifting as well as time scaling. So y of t x of at plus b. So this is what is called the affine transform of the independent variable, where you not only scale but you also shift. And there are other possibilities of transforming the independent variable other than affine. Alright. There is what is called the Mellin transform, and in the Mellin transform you can compute the Mellin transform by replacing t by e power t, and if you did this, you are non-linearly compressing the independent axis, and then if you take the Laplace transform of the non-linearly modified signal, that will be the Mellin transform. Alright, so this is not the only thing kind of transform that exists, but as far as this course is concerned, these are the typical kind of operations that we look at. And if a were greater than 1, then this corresponds to time compression, right? And if a were less than 1, this would correspond to time expansion. And if a were negative, in addition to it either being compression or expansion, you have reflection. All right. Now, given y of t, which is the compressed or expanded, maybe even reflection is thrown in depending upon the value of a. Suppose you want to get x of t from y of t. Y of t is the affine transformed signal, and you want to get back your original signal. So this would correspond to what? Y of t minus b by a. All right, because wherever t is there, if you replace t by t minus b by a, you will get back x of t. So if y of t is, say, x of 2t, then x of t is y of t by 2. So given the compressed or expanded with a possible reflection and also shift, you can undo the operation of the affine transform and get back your original signal, right? The corresponding counterpart for this in the discrete time case is y of n is x of mn plus cap n. So this is the discrete time counterpart of the affine transform. And working on a similar analogy, if y of n is x of 2n, that seems like the counterpart of y of t equal to x of 2t. So in this context, suppose I have something like this. So this is n and this is x of n. And now I have y of n, which is x of 2n. Therefore, y of 0 is x of 0, and y of 1 is x of 2, right? So y of 0 is x of 0, y of plus or minus 1 is x of plus or minus 2, and so on. Therefore, y of n in this case, y of 0 is 0, y of 1 is x of 2, so I have this, and y of 2 is x of 4, I have this, and so on. So you see the picture that emerges. So this is what the time compressed signal is, compressed by a factor of 2. All right. Now suppose I have w of n, which has these values. Now let us look at z of n, which is w of 2n. All right. So z of n is, again, what's happening here is all the even indices are picked up, correct? And it's very easy to see that the picture that you get for z of n is this, and the immediate thing that strikes you is that z of n equals y of n, right? So this equals y of n, and the consequence of this is that suppose you're given z of n, which is the same as y of n, you cannot tell whether the sequence that it came from was x of n or w of n. So in sharp contrast with respect to the continuous time case, where given y of t as x of 2t, you can go back to x of t by expansion by a factor of 2. Whereas here you cannot. And the reason why this is happening is when you pick up all the even indices, you are simply discarding the odd indices. Once you have discarded the odd indices, there is no going back. Therefore, although this appears similar to compression in the continuous time case, there are important differences. And the reason why this appears similar to the continuous time compression is, suppose you had a waveform like this, and then if you picked up all the even indices, right? So this kind of had a something like this, whereas this has an envelope something like this. So this seems to remind you that this is compression by a factor of 2. All right. So in that sense, this seems similar to that. Now let us carry this comparison further and then look at the other counterpart, that is y of n is x of n by 2. Immediately you see that y of 0 is x of 0 and y of plus or minus 2 is the same as x of plus or minus 1 and so on. That is y of 2 is the same as x of 1, y of minus 2 is the same as x of minus 1 and so on. So there are no issues here. But then moment you talk about y of 1, this is x of half and this of course is, the value is undefined. Similarly, all the odd indices are undefined, they are not 0. Given this definition, purely if you go by this, all the odd indices are undefined. Therefore, if you look at this particular example that we saw, and for this sequence given here, if you look at the n by 2 sequence, that is y of n equals x of n by 2, okay, if you just focus on this, it does indeed look like an expanded version, but as it is, all the odd indices are undefined. But you can go ahead and then define y of n as like this. It's x of n by 2 when n is even, and then you can say it is 0 when n is odd, in which case the picture now becomes like this. But the point is, it is not quite the expansion by a factor of 2 that you thought has to be there. And later we will see that more processing is needed to go from this picture to the picture where all these samples are filled in. Okay, to have a picture that this is expanded by a factor of 2, similar to what was happening in the continuous time case, more processing is needed. Right now all you can do is, you can only fill in zeros, provided you define it like this, and then to go from the zero filled sequence to a sequence that looks similar to an expanded version, more processing is needed. Therefore, right here you see, when it comes to the affine transformation, there are important differences between continuous time and the discrete time case. Okay, we'll stop here for the day because we are out of time.